Hello and welcome back in this series about how to use openEMS solver in electromagnetic simulation. I'll present today the first example about how to use the openEMS solver to simulate the rectangular waveguide and find its response. Here our very first example is the rectangular waveguide. This rectangular waveguide has three main dimensions. A is the width of this rectangular waveguide in X direction, B is the height of this waveguide in Y direction, L is the length of this waveguide in Z direction. This waveguide is nothing but a rectangular box, hollow from inside, and the outer shape from outside is just a metallic sheet, just a thin metallic sheet. So we have here the red area representing the free space or air. Let us move now to the tutorial web page in the openEMS page. So we have now some introductional tutorials and some microwave devices and some antennas. First, we can start with the rectangular waveguide. We have at the beginning there is a rectangular waveguide.ems. This is the Matlab file. So just you can download this file and open it in your Matlab. And then you can find also the results for the S parameters in magnitude and Z the impedance and the electric field in time domain, how this electric field is changing throughout the whole rectangular waveguide. You can find this Matlab simulation file at the same folder you have downloaded before in the openEMS/Matlab/tutorials. Or you can find this file.m in the web page of the rectangular waveguide in the openEMS web page. By opening this M file, take care from the beginning that this file is the latest version for the openEMS. So the latest version for the most of the tutorials is version 33 or 34 as you can see right now. The first step is the initialization. Initialization includes three main steps. So the first step is setup simulation parameter, which are the constant will be used during the whole simulation. Then set up the FTD function, which is a function related to the temporal excitation and the boundary conditions. In the temporal excitation, the time domain excitation function has to be determined, and we can choose from sinusoidal excitation, Gaussian excitation, or custom defined excitation. And the boundary condition have to be specified such that they can cover the whole 6 domains in Cartesian coordinates. So 2 in X direction, 2 in Y direction, and the last 2 in Z direction. And the last step in the initialization process is the setup CSX function, which is related to the geometry itself. In this case, we have to initialize the meshing process so that the formed mesh can easily and effectively describe the whole structure. And we'll see now how these steps are implemented in the rectangular waveguide example. So here in the Matlab file, we can see at the beginning the physical constant, the unit equal 10 power -6, which is drawing unit in the micrometer, so all the units will be described micrometer range. And A, B, and length describes the dimensions of the rectangular waveguide. And the frequency range is the F start, F end, and the F naught represents the center frequency, and lambda is this speed of light divided over the center frequency. And the TE mode describing in here in this rectangular waveguide is the TE10. And the mesh length is lambda over 30 in 3 dimension X and Y and Z. Second step in the initialization is set up the finite difference time domain function, which is FTDT initiate FTTD. We can just go into this function in Matlab and see what's the argument in this function. So the variable arguments in this function is the number of time steps in the simulation, which is NRTS, and the end criteria, and maximum time, and coordinate system, oversampling, and multigrid. And here we can see a small example here. The finite difference time domain is initiate FDTD. So now it's describing here the number of times steps is 10 power 4. So second, the function is FTDD set Gauss excitation, and this is here the excitation process. This is the temporal excitation. So the Gaussian pulse in time domain with describing f node center frequency, and fc is half of the bandwidth. And returning back to the file, we can see f start plus f stop times half. This equals the f node, and the fc equal half f stop minus f start. The next step in the finite difference time domain setup is describing the boundary condition. So here in this example, boundary condition is a vector equal 4 zeros and then 3 3. So this is the sixth boundary condition in the Cartesian coordinates. The function can be described using finite difference time domain set boundary condition, finite difference time domain, and BC the name of this file. So here we can see in this function, this boundary condition can be described using numerical values from 0 to 3 or alphabetical values BEC, BMC, MUR, or BML underscore X. So, and there is an example that can describe both of them, and they are equivalent. The last initialization step is set up the CSX CAD meshing. So first, the CSX initiate CSX. This is the main function at the beginning, with initialize the CSX data structure. And then returning back to our example, there is the next one describes the mesh. So we have mesh.x, mesh.y, mesh.z, and every one of them equal the function smooth mesh line with a vector and mesh resolution describing the mesh resolution for each direction. So here we can go to the mesh function, smooth mesh lines. So the argument is line maximum resolution, ratio, and some variable arguments. First, the line, so given fixed lines to create the smooth mesh between, and maximum resolution is the desired maximum resolution, and the ratio maximum neighboring line data ratio. So it's by default 1.3 and it's recommended to be less than 2. So returning back to our function now, so to set up this mesh with these values, so the function CSX define rectilinear grid, CSX unit, and mesh. So through this function it's create rectilinear grid, and the arguments it's the delta unit and the mesh. The mesh is the name of this meshing process before. After initialization process, coming the port excitation or defining the port. In this example, it's a waveguide port. First, we describe the start and stop points for this port. So the start is defined by point related to the mesh. So the start is the mesh X, first point in X direction, first point in Y direction, and the 11th point in Z direction. And also in the stop, the mesh will be at the end point in X and Y, but the number 15 in the Z direction. So here we have to get something to speak about. As we have PML in Z direction, so we have to be far enough from this PML layers. And on the other hand, the mesh size in the Z direction, which is the same direction for the power transfer in this direction Z, at least you have to get 2 mesh to represent your port. Now the function that describes this port is add waveguide port. We can go to this function and see this variable arguments. So now we have the function add waveguide, CSX, and priority, and port number, and start and stop and direction, AB, and mode name, and excitation direction. So we have the priority as the priority of the primitives as we discussed in the introduction. Start and stop are the points for this port, and the direction, which is the direction of the port, 0, 1, 2, or X, Y, and Z, numerical or alphabetical. A and B as a rectangular waveguide width and height in meters. And the mode name is the mode, like here it's TE10, and the last one is the excitation amplitude. Here in this one is 1 represent 1 volt per meter. And if this excitation amplitude is described with the value 0, it means that this port is describing a passive port. Returning back to the file, so we have finished describing the first port, and the second port will be described by the same one, but without the value of 1, so it means this is a passive port, so by default the port is equal to 0. The last step in this setup process is set up the structure's primitives before running the whole simulation. In this step, we have to define our physical and non-physical structure primitives. In our example we have right now CSX add dump, and there is some argument and the start and stop, and at the end CSX add box with some argument. This dump box is used to save the whole values of the electric field or the magnetic field in the geometry described after this description, which is add box. You can check this function and their arguments as we have checked this before many times. Now coming to the last step, which is running this openEMS program. So we have to describe the whole 5 sentences every time in Matlab. And then you can run openEMS with the simulation path and simulation CSX XML file. For the post-processing and watching the results, we can see right in this example that here it's defined the port, this function calc port, with the calculation to the power from this port to calculate the S parameters. And also we can find the impedance at each port, and we can find the electric field and magnetic field at any point through the dump box we have described before. So here in this example is describing the S parameter, the impedance, and at the end is describing the electric field with time domain varying with time. And I'm going to run the simulation right now. So after running the simulation, there is some values you can take care while the simulation is being done. So here we can see the values at the end from the right. So there is some values in dB and another value in the exponential form, just to make sure that these values are always increasing in the negative part. So 0, then 3, then so now this means there is convergence in the calculation. So the first result, we can see the S parameters here, the magnitude in dB values, the S11 and the S21, and the next graph is the ZL, the impedance. It's the real value and the imaginary value, and ZL calculated analytically. And for the third graph, which is the electric field or the bar going through this waveguide. So you can see this excitation with Gaussian going through from the start to the end. By here we come to the end of this video. Hope it could help you in your simulation, and thank you.